So this talk is about refactoring to functional. I'm going to assume here, apart from the abstract, and you've probably read the abstract, you probably read the level that it says beginner. This is introducing a bunch of functional concepts. So if you've been doing functional programming for a while, please step outside right now and go find one of the other beautiful 11 tracks that are going on at the same time, which I find fantastic. This is my first time at Devnexus, and I'm really, really impressed with the amount of people and the amount of tracks. So my name is Hadi. I work for a company called JetBrains. Have you heard of JetBrains? Okay. I normally have the following policy in that if you enjoy my talk, fantastic, I represent the company. If you don't hold it against the company. Okay? So it's very, very biased. Right, so let's get started. What is functional programming? So I'm going to read this out. In computer science, functional programming is a programming paradigm, a style of building the structure and elements of computer programs that treats computation as the evaluation of mathematical functions and avoids state and mutable data. It is a declarative programming paradigm, which means programming is done with expressions. So, apart from the fact that I can read pretty well, what does that tell you? That's the definition of functional programming from Wikipedia, so it's 100% accurate, okay? Because Wikipedia is, the truth is out there. Now, there's a couple of points that are really important in that definition. Can anybody tell me what those points are? They're the ones that are highlighted in red and bold, okay? So we're going to try and concentrate on some of those points and see where it takes us. But before we do that, we are going to do this refactoring to functional, but before you do that, it's always important to ask why. How many of you are in the Agile space here? You do Agile, or you do Waterfall and we just call it Agile, right? Basically the same thing. Have you heard of this thing called the 5 whys? You've heard of the 5 whys? The idea is that, like, if a customer comes up to you and says, you know, I need this feature, they, instead of saying, okay, I'll go ahead and implement it for you, you ask them why. And they say, well, because. And you're like, because why? And it's like, well, because I need a list of customers. Yes, but why? Why do you need it? The idea is that eventually they'll give up and go away. No, the idea is that you try and understand better what the customer wants. And that works very well with customers. It doesn't work so well with kids. I've got kids, and some of them have started to learn this concept of why. And on the third time, you just shut the hell up because I told you so, right? I know if anyone's a parent, they know that they do that as well. But coming back to functional programming, why would we want to refactor to functional? So here's a few goals that I've kind of always tried to have during my time writing software. And I'm guessing that more or less they're aligned with your goals. The first one is that I try and write less code. And as I grow older, I try to appreciate more things in life and actually spend less time writing code, or aiming at the code that I write does the same amount of things that I used to do with more code. I like to write expressive code. And again, this goes back to initially, when I started out in this field, I thought the more obfuscated my code is, the better, because it makes me look smart. I'm sure that we've all had our colleagues that do something like that. I've learned that there are better ways. I try and write correct code, and this goes along with the whole thing of unit testing. How many of you here unit test? Okay, and how many understand what a unit test is? Pretty much everyone, right? Okay. And you agree that it's a good thing, yeah? It's kind of like always the same thing as like quitting smoking, right? I know quitting smoking is good, but I still continue to smoke. So I know unit testing is great, but I don't do it that much. When I started out on the unit test, there's this curve, right? The first time they show you a unit test, you're like, I don't need this. Then it's kind of like, well, this is actually cool. It allows me to like do this refactoring thing and keep my code great. Now I'm going to write unit tests for absolutely everything, including my getters and setters. And I'm going to now try and go for 100% code coverage. And I get to that curve where I'm just like, I'm sick of writing unit tests. And I start to come back down and say, if I could write less unit tests, better. Right? Have you been through that phase? Yeah? Okay, we've all been through that phase. So those that haven't, just jump to the let's write less unit tests. First of all, I actually favor, when I talk about unit tests, I favor integration tests as well over unit tests. I try and make them faster. But point being is that the less code that I write means the less code that I need to test. The more code that I use that other people write means the less code that I need to test. So I try and write correct code also. Also write performant code. Why? Because Silicon Valley, right? They've taught us that nowadays it's not important if you make a product that actually is useful. It's not important if you make a product that actually anyone wants to use. The important thing is scale. It has to scale. I'm being a little bit sarcastic here. I was born in England, so I'm quite sarcastic. And of course, we have to be part of the in crowd, because nowadays, if you're doing functional object-oriented programming, you're looked on badly, you're frowned upon. Oh, you're still in the 80s. How many of you have read the book Design Patterns? Right? 10 years ago, if you didn't read that, they would look at you and say, seriously? Now, if you read that, they look at you, they're like, seriously? So, have you noticed how we keep reinventing things? Anyway, so coming back to this functional programming, enough with the whys. Can I use any language? More or less, yes. I mean, you can use any language, but it does beg the question of what exactly is a functional language. So here are a few things that I've kind of found along the lines of what a functional language is. First of all, there's this concept of functions being first-class citizens. And this is an important thing because we want to treat functions as basic primitive. Those are going to be like our building blocks, and we'll see this throughout this presentation. We want to have this concept of higher-order functions. So everybody knows what a higher-order function means. It's basically a function that takes a function as a parameter or a function that returns a function. That's a higher-order function. How many of you are, or everyone here is a Java developer? Yes, no, okay, I don't want to really answer your questions anymore, just shut up and get on with it. Tough. In my sessions, you're going to have to answer, I'm sorry. But they're normally just yes or no. Okay, C# developers? That's a Microsoft thing, I'm sorry. Java, mostly Java, right? JavaScript? Okay, right. So you're familiar with Java 8, you're familiar with the concept of lambdas and higher order functions, etc. So lambdas allow us to be a little bit more concise. Then there's this thing of a top-level function with a little asterisk, which basically means you don't really need this, but hey, if you have it, it's kind of great. And the idea behind that is that in a language such as C# or Java, normally what happens is that you can't just declare a function, right? You have to have a static object with a static method, and then invoke that function, invoke that method. The top-level functions is the concept kind of like how you have in JavaScript, where I can just open a file, write a function there, and that's why we end up with the horrible system that we do with JavaScript. There's no namespacing or anything like that, but hey, you can do it. And also the concept of immutable data. Why immutable data? Well, we'll try and see what the benefits of immutable data are. So now here comes the thing, like what will I be using in this session? I'll be using a language that probably a lot of you have not heard of. How many have heard of Kotlin? Okay. Kotlin is an open source language that targets the JVM. It also targets JavaScript. Why? That's purely a marketing aspect. If you target JavaScript, you might get some hipsters on board. It's developed by us at JetBrains. It's open source, Apache 2, and at some point in our lives, we will release it. Main purpose is to try and provide a safer, more concise, expressive language that is 100% interoperable with Java. And when I say 100%, I really mean 100%. Why am I using Kotlin? Well, because I try and do talks on things that I use. And I like Kotlin, I use it, and that's why. You can use Java 8, you can use Java 7 to 5, adding these things called the functional Java. You can use Scala, JavaScript, Clojure, Haskell, F#, C#, OCaml, Lisp. Is there any language there that I have mentioned or I have not mentioned that somebody uses? Go. Okay. You can use Go. Well, I guess, I don't know. I'm not too familiar with how. Does Go have higher order functions? There you go. You can use Go. There is sometimes a question about people say, like, is JavaScript a functional language? I kind of respond to that in, if you consider JavaScript a language, then yes, it's partially functional. I really love to hate JavaScript. I mean, I use JavaScript, I use it daily, but I hate the damn thing, okay? And I don't want to go into my 50s having to write JavaScript the rest of my life, because then that means I did something seriously wrong. Any JavaScript fans here? You should always ask that before I start to dig into JavaScript. Come on, it's a language we all love to hate, right? But it's hipster. Okay, so basic function syntax, just so you get a better idea of what Kotlin is, how it works. And of course, this session is not about functional programming. This session is about me selling you Kotlin, which is free. So here what I have is a basic function which has a parameter. It uses, if you're old school, if you remember Delphi back in the old days and Pascal modular 2, it uses that notation of parameter name colon string, parameter type. It's statically typed. So here I have a basic function that takes a parameter of type string, returns a parameter of type string. Here I have a single line function, which is a more concise way of writing the function. Here I have a higher order function, which takes another function that takes as parameter an integer and returns an integer. And last but not least, I have this lambda expression at the bottom, okay? Kotlin has a lot of type inference, so you don't have to be explicit about everything that you type. If you've done anything, if you've worked with Groovy, or with Scala, you'll find some similarities between Kotlin and those languages. We normally don't ship with the kitchen sink. So, higher order functions. We have a sum here where basically this is a shortcut for a function sum. Here's a shortcut for a function multiply. And then here I have a function calculate, which takes as parameter a function that takes two parameters and returns an integer. So basically what we saw before here is how I can call it. So there's a couple of notations in Kotlin which you'll see throughout this session. The colon sum is basically calling the function by name, similar to how you can do it in JavaScript without having to put the colon. So here I'm just calling the function by name. Here I'm passing in a lambda expression, anonymous function, and here I'm passing in another lambda expression with type inference. Okay? Very simple, right? Everyone understands that? Very easy to read, which is one of our goals as well. Make it so that anyone that does Java can pick up Kotlin in a day. Okay? So if you've picked that up in 1 minute, that's great, right? Okay. Pure functions. What is that? So given some input, function always provides the same output. And more importantly than that, the idea of pure functions is that it doesn't have any side effects, right? So what that means is that basically the function is idempotent. So every time I execute it, it will always just do the same thing without affecting anything that's going on around us. In the sense that it's not going to mutate some state. It's not going to alter some object. It's not going to do anything like that. Now you wonder, why is that? Well, if I take a function that all it does is just calculate a value, it's easier for me to reason about that function. I don't have to worry about all of the consequences of executing that function and how it alters the state of my project. Consequently, it also means that I have less to worry about when I do unit testing, right? To understand what a pure function is a pure function has to kind of have this referential transparency, which basically means that if I take that function out and I put in a table lookup, it does exactly the same thing. So really, any function that is pure can be replaced with a table lookup. That's what referential transparency means. And the idea behind this is to try and reduce all of these moving parts, is to try and reduce the fact that when I call a function, something happens somewhere that I'm not aware of. So we try and aim for these pure functions. So having said all this, can we achieve our goals? So, I want to write less code. I want to write more expressive code. I want to write correct code. I'm not too worried about the whole Silicon Valley scale factor because, most of my users aren't 100 million users on every minute. But the other things are always important to me and always have been. So let's see if we can get somewhere with this. So here's a function. And can anybody tell me what this function does? It's a trick question. Okay, why is it a trick question? Because there's the answer. Okay, what does this function do? It does something. What is that something? It wasn't a trick question. That was a joke. Never mind. the only way for you to detect what this function does is how? You have to read through it, right? You have to read through it, and you have to reason about it, and try and decipher the for each loop. You've got to decipher the conditionals to try and figure out what that function does. Because the only indicative of what that function would do to aid you would be the name. If I give it a really, really bad name, which we're all guilty of, right? That's what we do best in our code, is give things bad names. You don't know what that function really does. Now, if I show you this function, can you tell me what that does in an easier way? Is it more simple to figure out what that does? You have to say yes at this point, because if you say no, my whole session will be like void. It won't matter. So I don't care even if you say no, we're just going to assume yes. Okay? Seriously though, it is. I get a list of elements, I group them, okay, some syntax weird thing which I'll tell you about in a minute, and then I map that to a new value which is a pair of two values. So basically, I'm taking a list of elements, grouping them by an element, and then creating a new pair. So I'm basically counting the list of elements, the appearances for each element, which is what I'm doing here. The difference is that this one is much easier to reason about, right? And there's nothing magical about that. There's nothing like, what's functional about that? Well, actually, it depends what we consider functional, right? And then that's what we're going to try and show. So let's go step by step. Here I have a loop, okay? Here I have a list of albums, which I'm hoping you recognize that that's Pink Floyd, the real Pink Floyd, before Roger Waters left. And I have a function here that says top US and UK albums. The V1 is just the version 1. So what I'm doing here is I'm taking a list of the albums, and I'm iterating through the number of albums there is. I'm checking to see if they hit the number 1 in the UK and the US. If they did, I add them to another output list. Okay? Now, if you look at this code, I've got a lot of those moving parts, right? I've got this variable here that's got a list of elements. That doesn't have moving parts. Well, it will eventually as I add things to it. I've got this loop, which I have to reason about the length of the albums and all of these things. So what I can do is start to remove some stuff. So I can start to remove some of these values, some of this state, some of these moving parts. So the first thing I'm going to do is I'm going to move away from counters, and I'm just going to move into this concept of, you know, for each kind of thing. For every entry in this, loop through all of the entries. Now, this isn't magic. This is just a construct that a language provides me. It can be a syntax, it can be a keyword of the language, or it can be a function of the language. All it is a construct. So all I've done is just get rid of that having to reason about the integers and the counts. The next thing I do is I'm going to say, okay, chart UK, chart US equals 1, add them to the album, right? Not much, but I've just got rid of the counters for now. Now I'm going to add what some people call syntax sugar, okay? So what I've done now is I've taken that for each, and I've created a function. And inside that function, I've now said, if chart UK plus 1 equals hits add. So what have I done? Basically, I've converted that for into a function. So what's functional on that? I've just created for each. What is for each? Okay, so let me explain this a little bit so that we're on the same page. This is a function that takes a function. Okay? In Kotlin, if a function takes a function, if the last parameter of a function is a function, you can drop the brackets. Okay? So I can just pass in an anonymous lambda. That's just a lambda expression. Okay? And I can drop the brackets to make it a little bit more fluent. One of the key things of Kotlin is to be able to write nice DSLs. So by dropping those brackets, we can try and create a nicer DSL. But all that is just a function that takes a function. So we've already introduced some aspect of functional programming, which is what? Higher order functions. We now have functions that take functions. But there's still emphasis on the how as opposed to what exactly I want to do. I'm still got this predicate. I've got to look through this predicate and figure out what I want to do. So why don't I create another function that does that for me? And I'll call that filter, right? So filter now is a function that takes a function. What is that function? Another lambda expression. What is that lambda expression? It's just a predicate. Okay? That's all it is. Just a predicate that does that condition. So I've reduced that loop, I've reduced all of that to basically a single line of code that's just telling me I'm going to filter on a specific condition. Now, sometimes the data that comes out is not the way that we need it, and we need to adapt that data, and that's where all of the map and those things come in. If you look at the top US and UK hits years, in this version, what I want to do is I want to go through the albums that were hits in the UK and the US, and then for each of them, I'm going to create a new result, which is the year in which they were hits. So now I'm no longer just saying I've got a list of values and I want to filter on those values. What I want to do is take that list of values, filter on it, and then convert it to something else. Okay? But the problem is that I'm going back again to this whole concept of, here we go again, let's loop over all of this. Okay, it's passing in a function, but can I do it in a better way? Can I write less code? All I want to do is write less code. Yes, we can. It's called map. What map does is take an input and maps it out to a different output. Right? So what I'm doing here is I'm saying filter on these albums and then map it out by a new value. What is it? That's another convention, which is, if you're familiar with Groovy, you're familiar with, it's the same in Kotlin, that if a function takes a single parameter, you can refer to it by it. I could as well just put here x arrow dash greater than x, but I can also just refer to it as it. Okay? So we're all following, right? That's pretty simple. And all I'm doing really effectively is just taking functionality out and replacing it with functions, creating these building blocks. So of course you can take this a little bit more involved. Like here, for instance, I have a list of, I have albums, and then for each of these I have tracks on that albums. And what I want to do in this case, for instance, is get the album and the track lower than a given number of seconds. So again, I do a list, I do a for each, I then get the actual album. For that album, I look at the tracks, I filter them, and then I map that to another list, and then finally I return that list. The problem here that what I'm having is I don't have a list of elements. What I have here, I have a list of elements, each of which are composed of also elements. And there's a function that allows you to basically take that kind of input and flatten it out into a single list of output, which is called flatmap. So it's similar to map, but it's called flatmap. And what I do here is I take the album, I filter on the values, and then I do a map, and on that I'm doing a flat map. So again, I get rid of that loop. I get rid of that iteration. So what I've just done basically, the for each, the map, the flat map, the filter, all of these are just now functions that are provided to me by a language or by a library or by a platform. So I'm now writing less code. I'm trying to write more expressive code. What part of that is functional? The only functional aspect of it is that I'm now using this concept of higher order functions. So I have this concept of being able to take a function and pass in a function, or take a function and return a function. That's it. That's what I'm using right now. So if we go back to the original example, you can see that here I have the function that we saw initially, but now it's got a name, group and count repeated elements, and the one that is more clear doesn't even have a name. It does something. But if you look at these two, you kind of see that this one is easier to reason about and easier to understand. And not only that, and this is an important point, what it allows me to do is introduce a somewhat separation of concerns at the code level. So I'm saying there's code here that is interleaved. There's code here that has to do with creating a new list. There's code there that has to do with filtering. There's code there that has to do with transforming an operation. And they're all interleaved between the lines of code. Here, I'm basically separating all of these out into different lines of code. So I'm applying that concept of separation of concerns at a line-by-line level of code. Okay? You're all following, right? Okay, good. Any questions? No, great. Let's move on. I'll ask questions at the end, don't worry. So let's apply some of these techniques to common scenarios. I mean, it's all great with a simple example, but how can we use this in our everyday life? I mean, the purpose here of refactoring to function is to try and provide value, not just to say we do functional programming. So here's a customer search pattern, okay? Here's a class which is called customer filter that takes two methods, which is filter by name, filter by country, and basically the code is exactly the same. It loops through a list of customers, and the only thing that changes is the predicate, the condition by which we want to search for. I call this class customer filter. You probably have seen it in the wild, more commonly referred to as customer repository, which is actually the wrong name for a repository because a repository pattern doesn't have filter bys. Okay, it just implements a collection. But we've seen all this code. And we have lots of code like this, whether we use nhibernate, hibernate, all of this. We try to create our DAOs that do all these things. We can change this. We can cut down this code. We can just make it simpler. We can just do filter by predicate. So here what I'm doing is I have a customer. I have a list of customers, and then I have an actual predicate. And what I'm doing is the same code. Here I'm still using a for each. We can create a more approach using the same techniques as before. But basically what I'm doing is here, in this case, I'm just passing in the predicate, right? So I'm evaluating the predicate. So I'm cutting down the boilerplate code, just reducing the amount of code that I need to write. Another common pattern that we use, and this is in the design guideline books, is a template pattern. You're all familiar with the template pattern, right? I have a basic abstract class in which there is a method that has to execute a series of operations in a specific order, and many classes implement that kind of functionality, but they all implement different functionality for all of those different calls. So here I have an edit that does a check permission, edit record, persist data, but then persist data, edit record, and edit record, persist data are different based on the actual implementation. So that's left to the implementation details. What am I doing here? In essence, all I'm doing is just modifying the behavior of some code. That's all I'm doing. So why don't I reduce the amount of boilerplate code that I need to write with this to just a simple function that takes two functions. One that is for editing record and one instead for persisting record. All I'm doing is just modifying behavior at this point. Nothing else. So why have all of that boilerplate code? And we can take these techniques and we can use them for more interesting things. If you're familiar with, for example, C#, which you also have this in Java, which is try with resources, try finally with resources. Here I have a closable object, so I create the closable object, I do something with it, and then I finally close that object. Okay? How do I guarantee that people close that object? How do I guarantee that someone is going to actually do object close? The day they said that we have managed code, we stopped free and kneeling pointers. We just said, oh, managed code is going to take care of everything for me, except resources. So how can I do that? I can actually use the concept of functions to try and provide something like that. In Kotlin, we don't have this statement of try with resources or the equivalent in C#, which we'd be using, but I can create a function that does it. So I have a function called using, which takes a closable and then the actual body of the code. And then what I do is I do a function call and then finally close. Right? And then when I want to use it, I just say with closable object, using the object, I can drop the parenthesis to give it a much more cleaner DSL-ish approach, and then just execute the block of code. Now, I'm using this with a try with resource finally, but you get the picture that you can try and implement these methods for different types of things that you could potentially have in your code, right? Just using functions and passing functions as primitive. Here's another example of when it takes place. Now, you know Go. In Go, there is a defer, right? Kotlin, we don't have a defer, but again, we can use something like a function to implement that functionality, which basically here what I'm saying is that with defers, print line, then defer this print line. So this should actually happen last and then print line B. Just implementing it with a function. Because now I have the ability to allow functions to be passed in, behavior to be passed in, and I can start to play with that. And that's very, very valuable. Without the ceremony, if you think of like, for example, the strategy pattern, a lot of times, why do we go to the whole ceremony of creating a strategy pattern? Why are we doing it? We create a strategy class, and then we have like different sorting algorithms, and then we instantiate these algorithms, and then we pass in these classes only for the sole purpose of changing the behavior of a specific algorithm. That's it. And we go through all this ceremony. A lot of times we're not maintaining state. Right? We're not. We're just changing behavior. So this is the strategy pattern for a sort algorithm. I have quick sort, bubble sort, sorter. What I can do is just say, Okay, sort in a functional way. So I just pass in the actual code that does the sorting. Now, one of the things that I toppled on when I came to, started to embrace it a little bit more, shall we say, functional programming, is the concept of dependencies. Okay, so you're all familiar with dependency injection, and you're all familiar with that. Here is a typical example of a customer repository where I have a data access class which does a whole bunch of different functionality, and it delegates a lot of this functionality to the actual data class that is being passed in. Everybody here familiar with dependency injection? Right? Okay. You've all done your Spring with your XMLs, right? Everyone. We've all done it. Now let's think about those dependencies in these classes. Tell me, is this a scenario that you've ever encountered? If you've done any web development, MVC, any type of web framework, you didn't have this concept of an MVC controller where I have, for example, a checkout controller. And I have a checkout controller, and I have a bunch of different methods on that, and then I'm passing in a bunch of different dependencies on that checkout controller. Each of these doing different things, okay? How many of you have done this, or something similar? Have you ever noticed, where sometimes you're passing in 3 or 4 dependencies to a class, and then each of these methods are only using one of those dependencies? So you start to wonder, what the hell am I doing? Why am I encapsulating all of this functionality under a single class and then not really using these dependencies across the class? That, unfortunately, a lot of times is forced onto us because of a framework, right? If you take, for example, in .NET, and I'm sure that in Java is the same, a lot of frameworks say, oh, you want a checkout controller that maps to a URL checkout? You're going to have to put all of that crap into a single class called checkout controller, or die configuring the routing table, right? So it's forced onto us. And then we end up with these long dependencies being passed into the classes for no reason. So how do we deal with these dependencies? I mean, what do we do? Well, first of all, how many of you use an IOC framework? Okay, inversion of control. So we came up with this miraculous framework which said, do you need a dependency? Right, first of all, break up your classes into smaller classes and pass in those classes, pass in those dependencies. Invert control over those classes. So instead of my class creating and instantiating a class that it depends on, I'm going to pass it in. And then we started to write all these long chained calls to instantiate one class, which had 60 embedded instantiations. And someone said, no, you don't need to do that. I've invented this thing called an IOC container. And it automatically wires things up for you. And then what did we do next? Like all great developers, we abused the system. And we said, okay, now I'll pass in 15 dependencies, right? And now we've got classes saying this, the one class has 15 dependencies passed in, and people are like, oh, that's the fault of the IOC container, because that's what we do as developers. If we do something wrong, if we abuse something, we blame that something. We say it's the tool's fault. No, it's not the tool's fault. It's your fault for abusing the tool, right? So what is the solution to passing in multiple dependencies in a class? Passing in a collection? No. The issue that we have here a lot of times in our code is that we're violating the single responsibility principle, just in a different way. Instead of having one class do many things, we have one class depend on many other classes. So that tight coupling actually exists. That class is orchestrating a whole bunch of things. The difference is we don't call it tight coupling because it doesn't depend on a specific implementation, but it still is a tightly coupled system. What's missing there is a layer of abstraction a lot of times. We have to separate up those classes into multiple classes. But I've encountered this situation, so how do we deal with these dependencies? How do we pass in behavior in a functional approach? Well, we just pass in the function. Instead of all these classes with all these functionalities and having to worry about IOC containers and all of this, all we do is just pass in the behavior. That's all we do. And there's techniques that we'll see in a minute that allow you to make this in a kind of like a cleaner way. Okay? So let's start to think a little bit about this functionally, or thinking functionally. And if we look at all the examples, what we're doing basically is we're using this concept of functions as our primitives. So we've gone from using objects as primitives to just using functions as primitives and treating them as first-class citizens. We're saying you exist as an entity without an object associated to it. Now, given that some languages require that technical detail, but we're starting to, that's an implementation detail, but we are thinking about functions as behavior. And all we're doing is basically we're just combining these functions. That's all we're doing. We're adding function to function to function, function passing function. That's all it is. So we have functions that take functions, such as filter. We have functions that take a mapping function, which take one function that maps one input to an output. We have functions that do a lookup or a group by and things like that. We have functions that return functions. So here I have a function filter that returns, in this case it doesn't return functions, but I have filter map group by, and all we're doing here is basically just pipelining. And this is not a new concept. Pipelining has existed for years. Martin Fowler, I think, recently blogged about it again, but this concept of pipelining has existed since the Unix days, right? Just taking input, processing it, and sending it to the output. Now, what will happen eventually, I think, that as functional programming in Java and C# and all of these start to catch on. By the way, C# has had functional programming, functional constructs for a very, very long time, except they didn't call it that. They called it LINQ. Have you heard of LINQ? Language Integrated Query, which basically gave you the ability to do select statements in C#. And they focused it around selecting database code and things like that. But really, all it is functional constructs, right? Select, map, group, all of these are the same thing. So what's going to happen eventually is that we'll probably end up at some point with, and I'm already seeing it, is like a line with like 60 different functions pipelined. And then we go back to, what did we just do? We abused the system. We said, okay, we'll just chain everything together. We shouldn't do that either. One of the purposes of this, one of the most important purposes of this is what? To reason about code, to write less code, to write more expressive code. So I've already seen code like function after function after function after function after function. You're like, okay, what exactly is that doing? I've got to now, in my brain, mentally go backwards and figure out what that's doing. Don't do that. And also, please don't introduce temporal variables to give things name. What can you do instead of having 15 function calls? You can refactor out to what? Another function. So when you have 7 calls of pipelines, maybe it makes sense to extract 3 of those functions into another function, give it a more descriptive name, right? We can still apply all of these refactoring techniques. And then we can, of course, reuse that, right? But there's more ways that we can actually reuse functions in functional programming. Now, some of the things I'm going to show you now, a lot of languages have first-class support for. Those that don't, you can work around them. It does provide you with it does give you a little bit more boilerplate code that you have to use, but nonetheless, you can still do it. Composing functions, function composition. So here, I have a sum that takes an int and an int and it returns the sum of it. And here is a squared, which takes an int and squares a number. If I want to compose this functionality, what I'm not going to do is go and create a new function that's called sum squared and re-implement the code. It would be ideal if I could actually use the code that I have, reuse code. So what I can do is create a function called compose that takes sum squared and creates a new function. Because again, we're thinking about functions as primitive building blocks, right? Obviously, there needs to be a condition to be met there, which is the output of the type. The type output of the first has to be matching to the other one, the input of the second. But apart from that, no other requirement. Now, Kotlin doesn't come with a compose, first-class support for composition. But that's just a compose method, or just a compose function that you can create to do that composition for you. So what I'm getting back here is not a result. I'm getting back here a function called squared sum, which now takes 2 parameters, does the sum of them, and then squares them. Okay? Another concept which exists in functional programming is called currying. And if you've heard of, how many of you have looked at Haskell? Right, so Haskell curry. This is kind of where this comes from. And what currying allows me to do is, I have a function called sum, which takes 2 integers. And if I curry that, what that is going to give me back is a function that only takes 1 integer, 1 parameter. So basically what currying is doing is when you curry a function with more than one parameter, it's going to give you back a function slicing up those parameters. So now, if I want to call curry of the initial one, I do sum curried because this is a function that takes a single parameter, and on that, that's another function that takes a single parameter. So basically, it's taking a function with multiple parameters, and from that, creating functions with single parameters that you then chain to eventually call the value, the result you want to calculate. Again, Kotlin doesn't have support for first-class currying. Haskell does have support for first-class currying. All functions in Haskell by default are curried. I can create a function that just curries it. So here is sum curry, and what that does is creates a curry of that function. Here's another example with more parameters. So here I have a function with 3 parameters, and I curry it, and then I can call those as individual parameters. And the reason for this, why this is useful, is because we have this thing also that you can do in JavaScript. Actually, you can do this easily, which is called partial function application. So you're all familiar with the concept of default parameters, right? Where I can have a function, and the function can take default parameters, and then if I don't pass in those parameters, it calculates it with those defaults. What if instead of calculating the result, if I want to get back a function that provides default parameters? So whereas a normal function call with default parameters, if I don't pass the second parameter in, it just uses default, but it calculates the result of what I want to do. I want to get back a function instead of a result. I want to get back a function that I can provide default parameters to. And you can do that. And what is the purpose of this? Well, if we go back to that example of the checkout controller, I had that checkout controller, which I moved away from a class and moved into what I'd call just a simple function. And here I had a function that's passing in the behavior, right? Now, if every time I want to invoke this function, I have to repass in this behavior, it starts to become a little bit verbose. It's kind of like the same way as using dependency injection without using an IOC container. How could I make that easier? I can use partial application. So I can define new functions that already have predefined parameters passed into them, and then just use it that way. So here, for example, I have a handler, which is a checkout handler, making it a partial function and passing in cart data. So every time I use this handler, it's already got the behavior for my cart data passed in. And then if I want to use it as a test, for instance, and get data from somewhere else, then I would invoke the complete function call without using the partial value. So basically what partial function application allows me to do is define functions with default values and then reuse those functions anywhere in my code, right? Again, it goes in line with currying. Well, it uses currying, and then it goes in line with function composition, etc. So here's an example, another example of using partial function applications. I've got a sum, and then here I'm doing sum partial of 10. So now I'm doing a new function, which is any parameter I pass in, it's going to add 10 to it. So the result of that would be 15. Okay? And of course, apart from the function, now we've got this thing called data, right? If you think about it, our life is reduced to processing data. That's all we do. We're just taking data and processing it in stages. And if you drink whiskey, if you like whiskey like I do, then you know that's what whiskey is. It's just taking barley and water and producing this beautiful thing at the end, right? So all we're doing is just taking data and we're just processing data. So what is our data? We have customers, we have invoices, we have points, we have ages. And what type of data is this? We have scalars. So we have age, date of birth, etc. We have collections of abstract data types. So we have list of customers, list of invoices, a set of pairs, what have you. And a lot of times we take these as inputs lists and we do outputs as lists, right? And if you look at it, all of those common operations that we've been doing are just taking collections of items. So map takes a collection of items. Flat map takes a collection of collections. Find filter takes a collection of items. Find all returns a collection of items. Merges 2 collections of items. And these are just functions that are operating on lists. And we're going to start to think about always working with lists, because that's all we're doing. We're just basically working with lists of data. And of course, from this list, we can also obtain scalars. So for instance, I could do a first, which returns the first element of the list. Last returns the last element. Find finds a specific element. Aggregate aggregates the results of the list. A lot of all of these functions that we see actually boil down to very few functions in functional programming and implemented with things called fold and reduce, which is a variation of fold. How many of you have heard of fold? Right. So fold is this thing that you read and you're like, what the hell exactly does this mean? Let me show you. It's really, really simple. Fold is, I have a function that takes two parameters where x is an accumulator, it's an initial value, and y is an element in this list. Okay? So now I'm going to represent the x as a circle and y as the square coming from the list. That produces another value. I now take that value, so basically what a function is going to do is take an accumulator and a list of values. I take that value, it gives me a result. With that result, I apply the same function again to the next element of the list. So on and so forth until in the end I get the result. That's it. That's all the mystery behind fold. All it does is just apply a function on a list with an initial accumulator. What is the difference between reduce and fold? Reduce has the initial accumulator of 0, right? An initial value. And why do I bring this up? Because if you think about it, a lot of times when we talk about functional programming, of course, one of the biggest topics is recursion, right? We need recursion for functional programming. So if you think about recursion, let's take a look at this example. Here I have the recursive maximum, okay? So I've implemented a maximum which takes a list, and what it's going to do is give me back the maximum number from that list. So if it's 0, it will give me a legal operation. If it's 1, it's going to return the first element of that list. If it's else, it's not, it's going to do a max on the first element of that list and the maximum of the remainder of the elements of that list, right? It's a recursive way of defining maximum. If you think about that, basically what I'm doing is I start with an initial value and then I apply an operation on a list of elements. Now, we all know that recursion isn't the best performance. How can we actually convert that to using something like what we just saw? That maps to a fold. That's all it is. If you think about it, a lot of the pattern matching with recursion is mapping back to functions such as fold and reduce. I take an accumulator of 0, and then I just iterate through the list and apply that function. In the case of maximum, I'm just doing the maximum between the two values, right? So a lot of the recursion ways that you look at the way that you can, recursion is somewhat of an easy way sometimes to approach a problem because we just take the input and we just apply a base value and then we reduce the value. All we're doing is, I just use the word reduce, we're reducing the input, and that can actually map to something like fold or reduce. I could implement this with reduce as well, right? One other topic that we brought up was this concept of immutability of the data. Now, why do we need to avoid state? Why do we need data to be immutable? So this is like its own topic, but first of all, if we start to treat things as infinite, then we don't have to worry about indexes and counts and stuff like that. And it enables us for other scenarios, such as, for example, lazy evaluation. And I believe Venkat has a talk on Java 8 streams and lazy evaluations. If you haven't seen it, I highly recommend you go and see that session. Because it allows us to now do lazy evaluation. So start to consume data as we need it and stop when we need it. It enables this other thing called reactive programming. And hopefully if you're still around after this session finishes, this afternoon at 5:30, I've got like the continuation of this, which is Introduction to Reactive Extensions, and we'll look at a little bit about that, look into that a little bit. So we can, if we think about data like to avoid state, we can start to treat things as infinite. And we have to aim for immutability, because if we really think about mutable data, all it's doing is introducing side effects to our code that we need to be concerned about. How many of you have heard of the concept of domain-driven design? A lot of you, right? And you say, okay, I'm going to create a customer. There's no such thing as a customer, right? So let's begin with, there's no such thing as a customer. There's like infinite representations of customers in a domain. But for the sake of argument, I'm going to create a customer, and then I'm going to add a whole bunch of validation code to this customer to check that the customer is always in a valid state. Have you ever done that? Right? Well, if you actually think about the idea of not ever being able to modify a customer, right, a customer class, a customer object, then, and if you combine that with the idea of anytime I create a customer, it is in a valid state, all of that checks for validation can disappear. Because as soon as I create a customer, it's in a valid state. Because if I couldn't create a customer, if I created it with invalid data, then it wouldn't be a customer. And a lot of times in domain-driven design, there is this concept of creating read-only properties or immutable properties that don't allow you to change values. It just makes things to reason about much simpler. A lot of languages have support for immutability. Scala has support for immutability. A lot of languages have support by default, things are immutable. In Kotlin, we have var and val, which is similar to Scala. Var means that it's mutable, val means that it's immutable. However, not all languages, including Kotlin, are capable of validating 100% that your code isn't immutable. So you have to take care about creating immutable code. So one of the things that always comes up, again, with functional programming is performance, right? And a lot of times, even myself, like I think about, okay, what is the performance impact of this? If I'm basically like going over to functions and just having functions pass in functions and functions create functions and recursion and all of this, surely this is going to have some impact on performance. Now, we are all guilty of thinking things like this and missing the bigger picture that sometimes, my database is a bigger bottleneck or my internet connection is a bigger bottleneck than my stack call. But nonetheless, it is important to know some things about performance. And I promise that I won't do Fibonacci, but there is one example. Here is Fibonacci. If you run this, something like 5, 10, 20 or something like that, it hangs. You can't. This is a recursive version of Fibonacci that is extremely slow, right? If you run the iterative approach, which, this is simple. If it's n, it's 0. If it's n0 or n1, return the value, else return n-1 plus n-2. Why is it slow? Because it's doing this call recursively and it's recalculating. A lot of times it's recalculating the same values over and over and over again. The iterative approach, tell me that you understand that if I didn't call that Fibonacci. You wouldn't, right? This is much easier to reason about. But if we have to end up writing code like this, it's kind of like, well, this sucks, right? Because, this isn't easy to reason about. So there is a technique that you can use which is called memoization. And this is a specific implementation, but you can actually make a generic version. And what this is saying is, if I have to make calls that are recursive, that calculate the same values, if we actually think about functions with referential transparency, that all it is just a lookup table, if I've already calculated a value, why don't I just look it up? This is memoization of the function Fibonacci. If you run this, it runs at the same speed as the iterative approach. Okay? There might be nanoseconds of a difference, but it's not, you can't see it with the human eye. Okay? And all I'm doing is just saying, well, let's treat as functions, pure functions, as what we said they should be, which is just a lookup table. Now, you can make a generic, generalized version of this using functions that I can pass in functions and look up the value before doing the calculation. I did a simplistic one just so that you see the Fibonacci approach. Another concept that often comes up is the concept of recursion and tail calls. So here, I have a factorial, and this does 0, 1, return 1, else return number times factorial number minus 1. Now, you're all familiar with what tail call recursion is? That the last call is recursive. The last call is to the function itself. This example is not tail call recursive. Why is it not? Because the last operation is not the call to the function itself, although it might appear so. The last call is to the function multiply. So it now has to keep all of those values, right? It has to compute all of those values. Now, in scenarios like this, when you want to avoid tail call recursion, what you can do is create a kind of tail called version of the recursion, whereby here I have this concept of accumulator. And again, this actually maps back to what we're seeing with fold, right? and I have a return accumulator and then return accumulator. And this, in this case, is the actual tail core recursive. And a lot of languages, including, for example, Kotlin, have, well, not a lot of languages. I think Kotlin is one of the few that has this ability to indicate to the compiler that a call is tail recursive. So when it is converted to bytecode, it will just replace it with a goto. Other things that you have to be wary about are inlining. So a lot of times compilers are smart enough to allow you to inline calls. So if I don't have to maintain closures on variables when I'm passing a function, what the compiler can do is, instead of call that function, is just take the body of that function and embed it directly in the function that it's being passed to. And that's called inlining. And that can have actually quite a significant impact on performance. Again, if we're benchmarking real performance of our code versus our application per se. So there are techniques that allow you to deal with this if you are aiming for that, performance thing. But again, if you're doing really high performance things, a lot of these things, a lot of good practices with object-oriented programming you couldn't even do. Now, what about all the scary stuff? Okay, if you've noticed, I've talked about functional programming, and I haven't mentioned a lot of those words that you've probably heard about mentioned. When I started to look at functional programming, I was a little bit reluctant to, because a lot of the community around functional programming, and I'm not saying this is a bad thing at all, but they love their things, and they love to talk about their monads and their monoids and their endofunctors and all of this. And how many of you know what a monad is? Right? There's a bunch of us that, there's a bunch of you that know what a monad is. I still don't know what a monad is. And there's the myth that goes around that once you know what a monad is, you write a tutorial so that nobody else can understand what a monad is. And it really is the case. I mean, monads aren't easy to understand, and there's been comparison to trying to explain monads with cats and with dogs and with pizza, and then there's been people that say, no, monad has to be explained mathematically. So yeah, let's put that aside for a minute. But you do come up with all of these terms, like a functor. What is a functor? I need to know what a functor is to do functional programming. No. My approach is the following. I didn't introduce any of these words to you. And I didn't introduce any of these words to you for a specific reason. Because I believe that any technique, anything that we try and do, has to provide value. You shouldn't get into functional programming because you want to know what a functor is, unless that's your job, right? But at the end of the day, we write software to provide value, and the majority of us are here to provide value to our customers, to our users, and not to say, look how cool I know what a monad is, or monoid is, or a functor is. And I believe that there's a lot of value in functional programming, and a lot of the things that I've shown you, hopefully you see that value too. That doesn't mean that we don't need to know these concepts. What I'm trying to say here is that we shouldn't let these concepts be the barrier for us to enter and to appreciate some of the things that functional programming provide us, and then once we're in, start to dig deeper and understand all of these. So some of these terms that we talk about, functors. Well, you've probably heard of a functor. A functor is a collection of A, whereby you can apply a function AB, returning a collection of B. Well, map is an example of a functor, right? What is an endofunctor? An endofunctor is a functor that maps over itself. These are all mathematical concepts, and they've got to do with category 3, but they're very, very used in functional programming and lambda calculus. What is a monad? Monad actually is kind of like an abstract data type that follows a series of conditions. It has a bind function. It has a null, not a null, an element value, and it has to apply a series of characteristics to meet the requirements to being a monad. What is so important about a monad? Well, monad was introduced to Haskell because Haskell is a purely functional language. It's probably the only functional language that is pure, in the sense that a purely functional language never has any side effects, right? Never. So what the hell is the point of a functional language that doesn't ever have side effects, right? And when I say side effects, means you can't read from the screen, you can't output to the screen, you can't do anything. You can just create amazing functions, but you can't do anything with the language, and that's what Haskell was, right? So Haskell needed this concept to be able to introduce side effects, but still comply with the aspects of Haskell which make it great, which is it's pure in the sense that you don't need to reason about potential side effects. And they introduced this concept of monad. And monad can be applied in everyday use that we see, which we don't even know we're using monad. If you're familiar with Scala's option, that's a monad. It says if a value is not null, then invoke a call on it. Enumerables, iterables, these are all monads that are implemented in C# and other languages. Promises is a kind of monad. So a lot of these terms that we don't even know what they are, we're actually using in our everyday lives. Okay? So to summarize, embrace functions as primitive elements. That is it. That's if there's like one of the big takeaways to this is start to think about function as your primitive building blocks, right? Start to treat them as what they deserve, right? Not just like just this thing that we don't consider because objects is the most fantastic thing. Focus on writing less your own code. A lot of these functionalities, map, filter, list, for each, all of these are provided by languages or libraries. It's not magic. If you drill down into them, there are for each loops. If you drill down into that, there are for loops with indexes and counts. None of it is magic, but it's abstracting it away from you. So you're dealing at a different level, which is functions, not moving blocks. Focus on write more descriptive code. And like anything, with functional programming, we can do it badly, and we can write horrible code, and we can write chained pipelines after pipelines that doesn't provide much value in terms of what exactly the code is trying to do. Focus on writing deterministic code. So try not to create functions that produce side effects. Because if they do, then you can't compose those functions easily. Then you can't reuse them. Then you have to reason about everything that's going on around you every time you invoke that function, which leads to more potential areas of surface area for testing. And it really isn't rocket science. I mean, don't shy away from functional programming because initially the concepts of monoid and monoids and monads and functors and all of this is alien to us. It really, we can learn all of those things. Okay. There's a few books that I recommend. There's a book called The Little Schemer, which is a very entertaining book. There's different versions. There's a little Lisper. There's a little Closurist. And it's basically like this mouse that's asking you questions and then answering itself in a two-column format. Very, very entertaining. Very good book. There's a website and a book that you can download. It's free. It's called learnyourhaskell.com. Of course, you have to learn Haskell. Now, Haskell is something that I shied away from at university, and I thought I'll never have to learn it in my life, and now I regret it because it's actually a very nice language. So I recommend that you look at Haskell if you are, looking at functional programming. And Venkat's got a very good practical book called Functional Programming in Java, which allows you to apply a lot of these concepts that I've covered in your everyday life. Okay? Everyday code that you write. And with that, we are done.